I think we are ready to continue the morning session. And our next speaker is Shota Komatsu, who will talk about crosscap states, integrability, and holography. So, please.
All right, so thank you, and let me thank the organizers, and it's great to be back to Budapest again. So yes, today I'm going to talk about integrability and crosscap states, which is based on the joint work with Joao Caetano, who is at CERN, and also work in progress with Joao Caetano and Leonardo Rastelli, who is in Stony Brook, and Paolo Soresina, who was a student of Luca Guriguolo and is now visiting CERN for 10 months. And I should also mention that there was also a nice related paper by Tomas last week, and also this morning by Ekman. Okay, so let me start right away by saying what is crosscap. So the crosscap state has been studied a lot in 2D conformal field theory in the past. So in that context, the crosscap state is defined as the following, in the following way. So you first take the flat complex plane, and then do the identification, z is equal to -1 over z bar. So this identification maps the exterior of the unit circle and the interior of the unit circle. And at the boundary, which is on the unit circle, you do the antipodal identification of points. So after you do this identification, the fundamental domain can be taken to be the exterior of the unit circle. And you can alternatively view this configuration from the point of view of radial quantization, and especially from the exterior point of view. Then you can view it as some kind of a non-trivial state created by this weird boundary condition. So in some sense, it's a kind of weird version of the boundary state. And as a result of inserting this crosscap state, so this is a typical notation for the crosscap state. As a result of inserting the crosscap state, the surface becomes non-orientable, and you can, for example, get Klein bottle or Möbius strip. Okay? So let me just say the punchline of the talk. So the punchline of the talk is that integrability, so the goal of my talk is to study crosscap states in massive integrable field theory, not in 2D CFT, as was done in the past. So the punchline is that integrability survives in the presence of crosscaps. And furthermore, the overlaps between the crosscap state and an excited state in integrable massive quantum field theory and also the spin chain can be computed analytically, and you can have some analytic formula for that. And furthermore, they compute one-point functions in n equals 4 super mils on real projective space, RP4, with charge conjugation. And there are also byproducts that we got from the analysis, but I don't have time to mention that. So this is the plan of the talk. So let me first start by explaining why studying crosscap is interesting. But before talking about the crosscap, let me first talk about something related, which is boundary. So in the past, the boundaries in 1+1 dimensional systems have attracted much attention. And one of the most successful examples is the Kondo problem, which is basically the following statement. So if you take some metal like gold and then experimentally measure the resistivity, then in the experiment, people observe that resistivity actually goes up. So this is what's called anomalous resistivity at low temperature. And Kondo basically pointed out you can understand this behavior by the following model, which is the free fermion plus magnetic impurity. And this magnetic impurity, he pointed out that is important for explaining this anomalous resistivity. And so this model by itself is 3+1 dimensional. But if you focus on the S-wave scattering of free fermion, you can do the dimensional reduction and then map it to 1+1 dimensional fermion with boundary. And furthermore, this system can be solvable by integrability or CFT, and they're having a lot of progress on this topic. And let me also just say that the same kind of physics also governs the famous Callan-Rubakov effect, which is about scattering of electron against monopole. And from high energy point of view, also the boundaries in 1+1 dimensional system is important because we know that the 2D CFT with boundary is related to d-branes in string theory, as Kostya explained in the previous talk. And more recently, there have been a lot of literature on the boundary state in CFT and spin chain, because you can use it as the initial state for the quantum quench problem. And even more recently, these boundaries in 1+1 dimensional system made appearance in n equals 4 supermills, as Kostya explained, for example, in the analysis of defect one-point function and determinant three-point functions. So now, let's move on to the crosscap. So in 2D CFT, there exists another important class of states. That is called the crosscap state. And this system is, the crosscap is important for analyzing 2D system on non-orientable surfaces like Klein bottle and Möbius strip, that, as I mentioned earlier. And also, it's also important in the analysis of 2+1 dimensional SPT phase with time reversal symmetry. But to me, more important motivation is to understand orientifold in string theory and also string compactifications. So one crucial difference between D-branes and what's called orientifold is that orientifold can have negative tension. And using that property, you can actually use it to construct DS vacua in string theory, and that kind of allows us to evade the no-go theorem, the famous no-go theorem by Maldacena and Nunes. However, if you look at the crosscap, if you try to understand the crosscap in massive field theory, especially in integrable field theories and spin chain, you discover that there is almost no literature for that. And that is the gap that I want to fill in my talk. And as we will see, the crosscap states in spin chain provide new integrable initial states for quench protocol, and it has interesting properties like long-range entanglement and the volume law of the entanglement entropy. And furthermore, the analysis in n equals 4 supermill suggests a new class of defects in general higher dimensional conformal field theory, which I would call orientifold defects. And I'm going to explain that as well. Okay, so now let's talk about the crosscap overlap in integrable field theory. I'm going to explain how to compute it. So the basic setup is this picture, which is the cylinder whose endpoints are capped off by two crosscap states. Although it might not be obvious, this is topologically same as the Klein bottle. So let's analyze this Klein bottle partition function in two different ways. So the first way to analyze this partition function is to expand in what's called tree channel expansion, which is to basically insert a complete set of states here and viewing R as a time direction. And if you do this expansion, you can express this partition function in the following way. So you have the overlap between crosscap and the energy eigenstate square, and then there is a propagation factor coming from this propagation of distance R. And in particular, if you take the limit where R goes to infinity, you can project this sum to this contribution from the ground state, because the ground state dominates the answer. So this is basically telling us that if you compute the partition function of the Klein bottle and take R going to infinity limit, you can read off the crosscap overlap as the prefactor. So let's go to the other expansion. So this is more interesting and complicated, which is called loop channel expansion. So in the loop channel, I want to view this L as time. But because of the crosscap states, it's actually a little bit more complicated than the boundary case. So let's talk about a constant time slice, which I denoted by red line. So this constant time slice, let's start from here and then goes all the way to here. Then, because of the crosscap identification, you have to continue the constant time slice to here. And then you can continue here, and then comes back to the original point. So this is basically telling you that the constant time slice is defined on the volume 2R, not R. So another peculiar feature is that if you take this red line and time evolve by L over 2, then you get this dashed line. And this dashed line is at the same position as this red line, so you are basically taking some kind of a trace. But as the arrow, directions of the arrow indicates, you see that the directions of the arrows are opposite. which basically means that you need to insert a parity operator before taking the trace. So in the loop channel expansion, what this means is that you get this kind of trace, which is like a trace of the system whose system size is 2r, and then you time evolve by -L/2, and then insert the parity operator. And if you write explicitly this trace using the eigenstate of the parity, then you get this kind of expression where this epsilon is basically the parity eigenvalue, which is -1 or +1. So far, the discussion has been quite general, but we know that in integrable field series, states are labeled by the rapidities of particles or excitations or magnons. In that case, by analyzing how parity operator acts on the rapidities, you can argue that this sum can be converted into this sum, which is basically sum over parity invariant solutions to the beta equation. So this is basically the effect of the parity operator insertion. And by equating the loop expansion and the tree expansion, you finally get this formula. So you do the sum over parity invariant solutions to the beta equation, and then take the limit r going to infinity. Then you can read off this cross-cap overlap as the prefactor of this exponential factor. So if you look at the left-hand side, then you can see that this is almost of the form of thermodynamic beta ansatz. The only difference is that we need to deal with these parity constraints because we are restricting the sum of our states to be the parity invariant states. So basically, we just need to understand how to deal with the parity constraints. So let's talk about it. So this is the expression that I had in the previous slide. And in order to deal with that, I will take the most direct approach, just write down the beta ansatz equation. And in this case, we need to be a little bit careful because the beta ansatz equation takes slightly different form depending on whether you have a zero momentum state or not. So if you don't have any zero momentum state, the beta ansatz equation for parity invariant states take this form. On the other hand, if you have a zero momentum excitation, then the equation takes this form. And now comes the crucial observation. So the crucial observation is that these equations are formally identical to the beta ansatz equation in the presence of boundary. So in the presence of boundary, people know that the beta ansatz equation take this form, where R is the reflection amplitude, which depends on the details of the boundary condition. If you compare this, and then you immediately notice that if you replace RP squared with SP minus P, then you get the equation for this sector, which I call S sector. And if you replace RP squared with this combination of S matrix, then you get this T sector. So this is basically telling you that once you do this identification, we can just recycle the result for the boundary problem, which was already solved by thanks to many people actually in the audience, and also including people not in the audience. Okay, so this is a review of the solution to the boundary problem. This is actually something Kostya already mentioned. So the idea is to now consider the cylinder with a boundary and then analyze this partition function in two different ways and solve it using thermodynamic beta ansatz. I'm not going to explain you how to derive this, but the final result takes this form, which is complicated. But the important point is that final result consists of two factors. So the first factor is some integral of y functions. And the second factor is a ratio of Fredholm determinants. But this Fredholm determinants is a little bit complicated than what you encounter in other contexts because the weight factor inside the Fredholm determinants depends on y function, which by itself is a solution to this nonlinear TBA equation. And furthermore, what's important for the application to the crosscap state is the following fact. So the only dependence on the details of the boundary state sits here, the factor theta. And as you can see, this is the only place you see the dependence on R of u, which is the reflection amplitude. And furthermore, you see immediately that if you replace this R of U by some S matrix, which is needed in order to apply this formula to crosscap state, then you see some nice cancellation between this factor and this factor. So this is already telling you that something nice happens if you apply this formula to the crosscap state. And this is the final result. So this one comes from the S sector, and this ratio of y function comes from the t sector. So the analysis is straightforward, but it's a bit complicated, so I'm going to skip it and just show you the final result. And again, this is the standard ratio of Fredholm determinant, which is identical to the one that I showed here. And so this is the prediction for the overlap for the ground state. But once you have a result for the ground state, you can also have the result for excited state, thanks to the two people in the audience, Patrick and Roberto. And basically, you just need to do some analytic continuation. And as a result of analytic continuation, you get some modified Fredholm determinant, which now the Fredholm determinants also contain some kind of like a summation piece in addition to integrals. And once you get this excited state result, then you can also analyze the asymptotic limit in which the volume becomes infinite. And then you can see that in the asymptotic limit, this integral just disappears, and then you are left with this summation part. And by rewriting this, analyzing this summation part, you realize that you can actually rewrite it into a finite dimensional determinant, and which very much looks like a golden determinant, but which is kind of formula Kostya already showed you. But one important difference is that here I just have a ratio of determinant, nothing else. So in this sense, you can view this crosscap overlap as some kind of simplest possible G function, at least mathematically. So this is the check we did. So we basically took what's called staircase model. So this is a very interesting model proposed by Zamolodchikov. We don't know the Lagrangian, but it is known that if you take this S matrix and then compute the ground state energy, then it shows a series of plateaux, and the values at plateau exactly coincides with the central charges of unitary minimal models, which basically says that this model actually goes through all, comes close to all the fixed point of those unitary minimal models, and flows in the IR to a massive phase. So we just took this model and applied this formula, and again we saw that also the crosscap overlap exhibits a series of plateaux. And if you compute the values at plateau, then it exactly reproduces the crosscap overlap for the A-series minimal models for the ground state, and which we also computed using the modular S matrix using the CFT technique, and both basically agree perfectly. Okay, so this was the story for the integrable field theory. Now let me just explain how to define crosscap states in integrable spin chains. So again, before talking about the crosscaps, let me go back to boundaries in spin chain. So there are two boundaries people discussed in the context of spin chain. The first is basically open spin chain, which corresponds to putting boundaries in space. So this is something people have been analyzing since the 80s. And there have been a lot of works about the integrability of open spin chain. However, what's more relevant to my story is what's called boundary states, which people started to explore about 10 years ago, I think. So this is some particular state in closed spin chain, and this is the analog of the boundary state in quantum field theory. And in the case of XXX spin chain, it takes this form. So you basically first form an entangled pair of nearest neighbor two sites, and then let's call it K of J, and then you just take a tensor product. So because it's defined in this way, this is almost a product state, and first of all defined almost locally, much like a boundary state in field theory. And the next important property is that it is short-range entangled, just because it's a product state of entangled pair of nearest neighboring spin sites. And because of this, it provides you an ideal initial state for the studying time evolution of entanglement. And in addition, people discovered that there is a simple formula for integrable spin chain, which is basically ratio of determinant and some prefactors. And now let's ask how to define a crosscap state in spin chain. So basically, as I mentioned in the beginning, the crosscap state can be defined by doing the antipodal identification. So the naive guess is to construct some kind of entangled pair of spin chain sides which are antipodally related, and then take a tensor product. And unlike the boundary state that I discussed earlier, which is basically entangled pair of the nearest neighboring sides, this crosscap state is long-range entangled. So if you, for example, compute the subsystem entanglement entropy and plot it as a function of lengths, then so this grows linearly until the subsystem size reaches half the system size, and then it starts decaying linearly. And whereas if you take a boundary state, it exhibits like this. So the entanglement entropy is always very small. And this blue line is a kind of typical entanglement scaling for high energy, highly excited state. And furthermore, you can actually show that this particular state, in the case of XXX spin chain, is annihilated by infinitely many conserved charges, which are generated by the transfer matrix T of u minus T of minus u. So this basically guarantees the integrability of this crosscap state. And furthermore, we also computed the overlap between the crosscap state and the beta eigenstate using Mathematica. And we found numerically, without a proof, that they admit a very simple determinant formula, which is basically similar to the formula that I derived from the quantum field theory. And again, the important point is that it is just given by ratio of determinant, nothing else. And so as I mentioned, this coincides with the asymptotic limit of the overlap formula for integrable QFTs. And it's similar to, but simpler than, the overlap formula for the spin chain boundary states. And I should also mention that this formula, we didn't provide a proof, but it was proven very recently, actually last week, by Tamas in a very nice paper. Okay, so this is basically telling you that having this analytic expression potentially allows us to compute some like a time evolution of this state, crosscap state, and maybe it provides us a new tractable initial condition for quantum quench, which is quite different physically from the boundary state because it's long-range entangled. So let me finally talk about how to relate this crosscap state to n equals 4 supermills. So this is a work in progress with Joao Caetano, Leonardo Rastelli, and Paolo Soresina. How much time do I have? Sorry? 18? 18, okay, that's too much. Okay, so, all right, so let's go slowly. So the claim is the following. The crosscap overlaps on the worksheet compute the one-point function in n equals 4 supermills on real projective space with charge conjugation. I'm going to explain what I mean by charge conjugation. So let me first explain what do I mean by real projective space. So the real projective space RP4 is in a sense like a 4-dimensional version of the crosscap. So you basically take R4 and perform this identification. Then as a result, the fundamental domain is exterior of this unit sphere, and you get some non-orientable space, which is RP4. And you can actually analyze correlation functions on RP4 and also write down some crossing equation. So if you consider a correlation function of local operator on RP4, there is a new conformal data, which is basically one-point function on RP4. So because RP4 identification breaks part of the conformal symmetry, one-point function of local operator is now non-zero. And the crossing equation schematically takes this form. So let's take, okay, actually here I'm taking the fundamental domain to be interior. but that's okay. So you take like a two operators, and there are like two different ways to perform the OP of these two operators. One is to kind of like do the OP directly by approaching two operators. And another way is to approach O1 to the mirror image of O2. So this leads to the crossing equation. And importantly, unlike the boundary state, which conformal boundary condition, which basically introduces new conformal operators, which are basically operators sitting at the boundary, it doesn't introduce new operator, and basically two channels are both governed by, in some sense, bulk OP. But the cross ratio are different because in one way, like you are approaching two operators directly, whereas in the other way, you are approaching two operators using the mirror image. Yes? Oh, okay. Yeah, so, right. So let's see. Yeah, I think it's, well, yeah, well, but important point is that on the sphere, like you are doing antipodal identification. So this probably like gives you an idea how it's related to RP4. Yeah, yeah, yeah. Yeah, it's a yes, yes. Okay, so then let's talk about, so far I was talking about the general CFT on RP4. So then let's talk about n equals 4 supermills on RP4. So in n equals 4 supermills, we can actually define a half PPS version of RP4 by combining this like a space-time identification with some Z2 identification of scalar fields, well, and also fermions, but it's a complicated, so I'm not going to write it down. But if you just do this identification, it turns out the final, the resulting, if you just do this identification and compute a one-point function, you discover that this leads to non-integrable setup. There is nothing nice happening if you do the computation of one-point function. So this is the result discovered by Joao and Leonardo in the paper which appeared this year. However, we understood that there is actually small modification that leads to integrable setup. And what is that modification? So this modification is the following. So integrability gets restored if we combine this and with another Z2 symmetry, which is basically charge conjugation of SUN. So instead of doing this, I'm going to identify phi 1, 2, 3, phi 1, phi 2, phi 3 to the transposition of phi 1, phi 2, phi 3. So here I'm using the fact that all the fields in n equals 4 supermills lives in the adjoint representation of SUN. So you can view it as a kind of n times n matrices. So this, I call it charge conjugation because I'm basically combining this identification with some kind of charge conjugation of the SUN generators. So these are, TAs are basically SUN generators. And if you do this identification, the scalar propagator on RP4 have a very interesting property. So there is one piece which corresponds to direct contraction. So this piece is just usual 1 over x minus y square, and also the like a double line notation is the usual one. So you just like connect the double lines in the usual way. But there is also a piece which is kind of like a weak contraction between the mirror images, and that gives you this factor 1 plus x dot y square. And in addition, because I'm doing this charge conjugation, if you try to write a double line notation, then you get some kind of twisted double line. And furthermore, if you want to compute a one-point function using this propagator, then you can basically ignore this part because this part is just a self-contraction which you remove when you define the local operator, because this part is also there in R4. And by defining like a local operator in R4, you basically remove the contraction coming from this part. So all you need to do is to do the contraction of one operator by itself using this propagator. Okay? And if you do that in the large N limit, you discover that the leading diagram is in some sense maximally non-planar. So you basically do the contraction of antipodal sides of the spin chain. So it's a little bit hard to see, but if you draw some other configuration, then you can immediately see that those are subleading. So this is basically telling you that the leading large N answer is given by antipodal contraction of single trace operator, and this naturally makes connection to the cross-cap overlap that I described earlier. So, and this is a conjecture for the asymptotic one-point function. So again, the conjecture is very simple. Well, actually, I'm missing square root here, so there should be a square root here. But the important point is that the form is very similar to the one-point function in the defect or boundary problem, but the only difference is that we expect there is no extra factors. And let me just explain for those who are not familiar with this expression. So this G is given by derivatives of logarithm of beta equation, and which is often called the golden matrix. And then this S determinant is some kind of defined by defining the Z2 grading structure. And this Z2 grading structure is dictated by the problem you study. And here we are taking the same Z2 grading structure as the defect one-point function because the symmetry structure is the same. But importantly, as I said, we don't have any, we expect we don't have any non-universal prefactors. Okay, so this was the conjecture for the asymptotic one-point function. But at this point, it's still a conjecture, and we are trying to do the one-loop check. We are doing the one-loop check of this conjecture. Yes, square root is missing. Yes, thank you, 4 point. Sorry? Because I forgot to write it. So you need square root. And so let me just mention also this new class of defects in Hardy. So one way to understand the RP4 is to use the embedding, what's called embedding coordinate, which embeds the R4 into 6-dimensional space with a null condition. And in terms of embedding coordinate, you can describe RP4 in this way. So you just identify x minus 1 with x minus 1 and x1 to 3, 4 to minus x1 to 3, 4. But if you phrase this problem in this way, then you wonder that there may be actually higher codimension version of RP4, which I'm just calling orientifold defects. For example, we can consider something like this. So also one is identified with plus sign, and the rest is identified with minus sign. And physically, this corresponds to some kind of higher codimension version of RP4. So the questions that I want to pose are, can we define them consistently in any CFT? So if so, what are crossing equations? And furthermore, in n equals 4 supermills, I expect there should be half BPS versions of these higher codimension versions of RP4. And combined with charge conjugation, they probably lead to crosscaps on the worldsheet, which preserve integrability and can be studied at finite coupling. So let me conclude. How much time do I have? 7 minutes. OK, very good. So the punchline is that the crosscap is integrable. And the overlap with excited state can be computed in both field theory and a spin chain analytically. And in some sense, it looks like a simplest possible G function. And furthermore, it's relevant for n equals 4 supermills on RP4. And we have a conjecture for the asymptotic formula at finite lambda. And we are doing one-loop checks and also SUSY localization. And so for the future directions, it's probably interesting to use this crosscap state and study some kind of quench dynamics. And in particular, because crosscap states is long-range entangled, it's interesting to see what happens if you start doing some kind of a measurement protocol, which performs the projective measurement. And in particular, it's probably interesting to see whether we can observe some kind of measurement-induced phase transition. And that's work in progress with condensed matter friends, Pieter and Yuan. And so far, the crosscap overlap that I discussed, especially on the field theory side, is only for the diagonal S matrix. And it's important to generalize the derivation to non-diagonal S matrices and also theories with bound states. And I should also emphasize that this is really the best arena for developing quantum spectral curve approaches to the correlation functions, because the final formula is just given by the ratio of Fredholm determinants. So now the question is how to rewrite the Fredholm determinants in terms of quantum spectral curve. And also, it's also interesting to try to find more examples of orientifold defects in n equals 4 supermills and general CFTs. And I just wanted to mention that in the famous paper by Guyot and Witten, which studied half BPS boundary conditions in n equals 4 supermills, some of them involve O5 plane, so that might lead to some kind of nice integrable setup. And finally, it's also interesting to study the crosscap for fishnet, which is kind of related to the talk by Eduardo we heard yesterday. And probably also for fishnet, crosscap might be actually simpler than studying some kind of D-branes and boundary states. And another comment that I wanted to make is that in the analysis of n equals 4 supermills, I mentioned that actually the diagram that contributes to the one-point function is actually maximally non-planar in some sense. So I would expect that there might be some Yangian invariance also for non-planar diagrams if it comes from some kind of crosscap type contractions. And that's the end of my talk. Thank you very much.
Okay. Thank you very much for this interesting talk. We have some questions.
Hi. So I didn't quite get, in the context of unequal 4 superior mills, you also have, thanks to this charge conjugation identification, some natural way in which the parity condition appears, so the fact that you probably would expect rapidities to come in pairs or to be 0.
Sorry, could you repeat the last part?
So whether you expect that thanks to this charge conjugation condition, you also get some parity condition on the rapidity.
Oh, that
like you had in the previous.
I see. So the charge conjugation on the well, I don't have a direct connection, direct way of connecting the two, but the charge conjugation corresponds to this twisting of the double line, which basically corresponds to like a changing the orientation of the string worldsheet. So, and then indeed, if you compute a cross-cap overlap, then there is a selection rule, which Kostya explained. So like only the states which are parity invariant have non-zero cross-cap. So there is an indirect connection, but I don't know how to make a direct connection.
Thank you.
Okay. More questions?
So what is the string counterpart of the orientifold theories?
Yes.
And why is it possible to see why your new orientifold, this the Walsh transposition, is better from the point of view of integrability on the string side?
Okay, so the Y transposition is better than without transposition. Okay, so actually, I didn't mention, but okay, so this is something discussed already by in the paper by Joao and Leonardo. So one important difference is that if you compute one-point function of RP4 without charge conjugation and the one-point function on RP4 with charge conjugation, then actually large N scaling is completely different. If you compute one-point function without RP4, sorry, without charge conjugation, then actually like a one-point function grows like N to some power, which basically indicates that the dual description is some kind of back-reacted geometry. And indeed, that's what they constructed in their paper. On the other hand, if you compute a one-point function with charge conjugation, and then it's order 1 in the large N limit, it basically indicates that it corresponds to some kind of probe. And indeed, our conjecture is that it corresponds to some kind of probe or one plane.
Okay. More questions?
Sorry, I probably should have read those papers you mentioned, but is it so obvious that n equals 4 really exists on RP4? I mean, you take rays in 5 dimensions, actually, right?
Mm-hmm.
And then basically every ray in 5 dimensions is a point in, you can say it's a point in in RP4. So locally it looks like R4, but then you have funny boundary conditions.
Yeah,
But
yeah.
is it, for example, clear? Have people looked at that the fermions don't cause problems with this?
Okay, so for this particular setup, I think we can actually show that this whole setup preserves the BPS, half BPS boundary condition. So because of supersymmetry, I expect it's well defined.
Okay. And related to this, is this some kind of, I mean, usually super Young-Mills is defined on Minkowski space, right? So what about the signature here? And also you wrote this inversion formula. Is it like Minkowskian inversion? Or
yeah, actually, yeah, that's a very good point. We were working on Euclidean space. So this inversion formula is the Euclidean inversion. And actually, precisely speaking, the holographic dual is a little bit different. It's like a Euclidean ADS5 times DS5. Because in order to preserve supersymmetry on the Euclidean space, you need to kind of like change the signature in the R-symmetry space.
So even the R-symmetry becomes non-compact, right?
Yeah. So it's actually O1 plane. So the conjecture is that it's actually O1 plane in Euclidean ADS5 times DS5.
And then the total supersymmetry left?
That's like 1 hard BPS. Yes.
Yeah. Okay. Thank you.
Okay, anything more? Kolja?
Thanks for the nice talk. So probably stupid question. So roughly speaking, you define the observable as having some Z2 symmetry generator and then projecting the state. So can you think about some like more general, I don't know, some if you also do some rotation at the same time when you identify, or like there could be probably many Z2s. Is there any criteria which of them would be integrable, for example?
Well, I expect like as long as it's Z2, you can basically combine it with this RP4 in Crosscap. So I think we can define like a different Crosscap states on the worksheet for every like Y reflections of the Dinkin diagram.
But can I ask, is your
Yes.
Crosscap state is always bosonic somehow? Or,
Yeah, I don't have a good way to answer that, but yeah, it's probably bosonic, but yeah, I haven't thought much about it.
Okay, Bogdan.
Thanks for a very nice talk. So, since these are really orientifolds, they should have some tension. Do you know? I didn't see any minus sign appearing in your one-point functions.
Yeah, that's a good point. Actually, determining the overall minus sign is a little bit complicated because we are always starting from this Klein bottle and then taking a square root. And when you take a square root, actually, like you cannot determine the sign just by considering the Klein bottle partition function. And so the quick answer is that so far we are unable to determine the sign.
But why not just consider the Möbius strip?
Yeah, that's a way to go, yes.
And then it should be fixed, right? For each, each kind of thing,
yes, it should be fixed.
And there's a prediction for what that is.
Yeah.
Okay, we're still on time, so we can have maybe one more question. Otherwise, I can maybe ask, is there any connection to any for super Young-Mills with alternative gauge groups? I mean,
you mean SON?
SO or SP, I mean, that's normal.
Yeah, so in some, yeah, so let me just mention that, like, so this, sorry, not this one, the other way. So this identification is what converts SUN to SON or SPN. Actually, like, there should be SPN version of this, although, like, we haven't explored this.
Yes.
And in particular, like, coming back to the last point, I think the one way to study kind of like a crosscap amplitude or crosscap type Feynman diagram is to study diagrams that show up in like a SON n equals 4 super Mills or SON fissionet.
Right. one last question.
Sorry, I may have missed it, but you were talking about the long-range entanglement in the spin chain setup, and I'm wondering if you did any analysis in the field theory. I mean, regarding these boundary entropy techniques or something like that. So did you do anything like
Sorry,
that?
can you speak a bit louder?
So did you do anything about the entanglement in the field theory, because you were mentioning it for the spin chains with this page curve. So did you compute anything in the field theory?
Oh, in the field theory, you mean like entanglement property? Well, I think I expect the same, but in field theory, well, the crosscap is a little bit singular because if you just take the overlap of the two crosscap states, then it diverges. So we probably need to do some kind of like a time evolution in the Euclidean domain, and then like I think I expect them to have a similar behavior.
Okay, let's thank the speaker once more and move on.